Welcome to today's session. In this video, we'll be exploring an exciting problem from LeetCode, problem number 525, titled Contiguous Array. It's a fascinating challenge that tests your ability to work with arrays and hash maps while developing an efficient solution. Let's dive in and break it down step by step. The problem we are tackling is called Contiguous Array. The goal is to find the maximum length of a contiguous subarray within a given binary array, nums, such that the subarray contains an equal number of zeros and ones. For the input, we are provided with a list of integers where each element is either a 0 or a 1. The output is a single integer that represents the maximum length of such a subarray. For example, if the input array is 0, 1, the output would be 2, since the entire array itself already has an equal number of zeros and ones, and its length is 2. Now, let's look at another example. If nums is 0, 1, 0, the output would still be 2. This is because the contiguous subarray, 0, 1, satisfies the condition of having an equal number of zeros and ones, and its length is 2. While 1, 0 is another valid subarray, the maximum length remains 2. Next, consider a slightly larger array, such as 0, 1, 1, 0, 1, 1, 0, 0. For the input 0, 1, 1, 0, 1, 1, 0, 0, the output is 6. This is because the subarray 1, 1, 0, 1, 1, 0 has an equal number of zeros and ones, and its length is 6, which is the longest subarray that satisfies the condition. Let's also consider the constraints for this problem. The length of the input array can range from 1 to 100,000, and each element in the array is guaranteed to be either a 0 or a 1. These constraints imply that our solution needs to be efficient, as the input size can become quite large. Finally, let's discuss a few edge cases. If the input array contains only one element, the output will always be 0, since it's impossible to have both a 0 and a 1 in a single element array. For example, if nums is 0, the output will be 0. Similarly, if all elements in the array are the same, such as 0, 0, 0, the output will also be 0 because there are no pairs of zeros and ones. On the other hand, if the array alternates perfectly between zeros and ones, the output will be the length of the entire array. For instance, if nums is 0, 1, 0, 1, the output will be 4, as the whole array satisfies the condition. To begin solving this problem, we can consider the brute force approach. The intuition here is straightforward. For every possible subarray in the input array, we count the number of zeros and ones and check if these counts are equal. If we find such a subarray, we calculate its length and update a variable to keep track of the maximum length seen so far. The steps are simple. First, iterate through all possible starting indices for subarrays. For each starting index, iterate through all possible ending indices. Then, for each subarray, count the occurrences of zeros and ones. If the counts match, we update the maximum length accordingly. While this approach is easy to understand and implement, it is not efficient. The time complexity is O(n) squared, because of the nested loops required to examine all subarrays, and the space complexity is O(1), since we are only using counters. However, the significant drawback of this method is that it becomes computationally expensive for large arrays, making it infeasible for inputs close to the constraint limits. Now, let's explore the optimized approach, which is both faster and more efficient. The key observation here is that instead of counting zeros and ones directly, we can track their cumulative difference as we iterate through the array. This difference, referred to as the balance, is sufficient to determine if a subarray has an equal number of zeros and ones. The strategy is to treat zeros as -1 and ones as +1, and calculate the cumulative sum of these values as we traverse the array. If the same balance appears at two different indices, the subarray between those indices will have an equal count of zeros and ones. To make this efficient, we use a hash map to store the first occurrence of each balance. This enables us to compute the length of subarrays in constant time. The steps are as follows. First, we initialize a hash map with the starting balance of 0 mapped to index -1. Then, as we iterate through the array, we update the balance by adding -1 for a 0 and +1 for a 1. If the current balance has been seen before, we calculate the length of the subarray and update the maximum length if necessary. If the balance is new, we store its index in the hash map. Finally, we return the maximum length found. This approach is significantly more efficient, with a time complexity of O(n) due to the single traversal of the array, and a space complexity of O(n) for the hash map. Although the optimized approach requires additional space for the hash map, it is a worthwhile trade-off given the substantial improvement in runtime performance. By leveraging the balance concept and the hash map, this approach scales efficiently with input size, making it the best solution for this problem. The chosen strategy combines efficiency, simplicity, and practicality. With an O(n) time complexity, the method ensures good performance even for large inputs. Additionally, the logic is straightforward once the idea of cumulative balance is understood, making it easier to implement and debug. The space usage is reasonable within the problem's constraints, as the hash map only stores balances and their first occurrences. In conclusion, the optimized approach offers the most efficient and practical solution to the problem. It avoids the inefficiencies of the brute force method while maintaining a clean balance between time and space trade-offs. This makes it the ideal choice for solving the contiguous array problem effectively. To solve the problem of finding the longest contiguous subarray with an equal number of zeros and ones, we can start with a brute force approach. The idea here is simple: generate all possible subarrays, count the number of zeros and ones in each, and check if their counts are equal. If they are, we calculate the length of this subarray and compare it with the maximum length found so far. To implement this, we initialize a variable max_length to track the longest subarray length and set it to 0 initially. We also determine the size of the input array, n, since we'll iterate through all possible subarray start and end points. The outer loop will fix the starting index of a subarray, and for each starting index, we initialize counters count_0 and count_1 to track the counts of zeros and ones for the current subarray. This sets up the groundwork for examining every possible subarray in the array. For each starting index of the subarray, we use an inner loop to iterate over all possible ending indices, effectively generating every subarray starting from the fixed index. At each step of the inner loop, we examine the current element of the array. If the element is 0, we increment the count_0 counter. If it's 1, we increment count_1. Once the counts are updated, we check if the number of zeros and ones are equal. If they are, we calculate the length of the current subarray using the formula ji+1, where j is the current end index and I is the starting index. If this length exceeds the current max_length, we update max_length to this new value. After iterating through all possible subarrays, the algorithm returns the value of max_length as the final result. However, this approach is computationally expensive. The outer loop runs n times, and the inner loop also runs up to n times for each iteration, resulting in an overall time complexity of O(n²). Despite its simplicity, this brute force method can be impractical for large arrays. The brute force approach, while straightforward, is inefficient because it repeatedly computes the counts of zeros and ones for overlapping subarrays. This redundancy leads to an O(n² time complexity, which is too slow for larger inputs. To address this, we can use an optimized approach based on a prefix sum technique. The key insight here is to treat zeros as -1s and compute a cumulative sum as we iterate through the array. When the number of zeros and ones is equal in a subarray, the cumulative sum at the start and end of that subarray will be identical. This means we can reduce the problem to finding subarrays where the prefix sum stays consistent. To implement this, we initialize a prefix_sum variable to track the cumulative sum as we traverse the array, a max_length variable to store the length of the longest valid subarray, and a hash map to store the first occurrence of each prefix sum. The hash map allows us to efficiently check for previously seen prefix sums as we iterate. As we traverse the array, we update the prefix_sum by adding -1 for every 0 and 1 for every 1 in the current element. If the prefix_sum becomes 0, it means the subarray from the beginning of the array to the current index contains an equal number of zeros and ones. In this case, we calculate the length of this subarray as I+1 and update max_length if this length exceeds the current maximum. If the prefix_sum has been seen before in the hash map, it indicates that the subarray between the first occurrence of this prefix sum and the current index has an equal number of zeros and ones. We calculate the length of this subarray using the difference between the current index and the index stored in the hash map. Again, we update max_length if this length is greater than the current maximum. If the prefix_sum hasn't been seen before, we store it in the hash map along with the current index. After processing all elements in the array, the algorithm returns the value of max_length. This optimized approach is much more efficient, with a time complexity of O(n), due to the single traversal of the array and constant time operations with the hash map. The space complexity is O(n), as the hash map stores at most one entry for each unique prefix sum. The prefix sum technique significantly improves efficiency by converting the problem into one of finding subarrays with the same cumulative sum. This approach eliminates the need for redundant calculations, as the hash map lets us quickly determine if a prefix sum has been encountered before. The hash map serves as a key data structure here. Each prefix sum is stored as a key, and its value is the index of its first occurrence. This allows us to efficiently calculate the length of subarrays without recomputing counts. Hash map operations, such as inserting and looking up prefix sums, have an average time complexity of O(1), making this approach both elegant and efficient in practice. By using these insights, we avoid the inefficiencies of the brute force method and make the algorithm scalable to handle large input arrays. When implementing this algorithm, it's important to consider edge cases to ensure correctness. If the input array is empty, there are no subarrays, so we return 0. Similarly, if the array contains all zeros or all ones, no valid subarray exists, and the result is also 0. In cases where the entire array alternates between zeros and ones, the algorithm should correctly identify the entire array as the longest subarray with equal zeros and ones. For single-element arrays, it's impossible to form a valid subarray, so the result is 0. By handling these edge cases, the algorithm becomes robust and capable of returning correct results across a wide range of inputs. This solution tackles the problem of finding the longest contiguous subarray with an equal number of zeros and ones using an efficient approach with O(n) time complexity. The key idea is to use a prefix sum where zeros are treated as -1s. This transformation allows us to reduce the problem to finding subarrays with a prefix sum of 0. We begin by initializing a dictionary prefix_sums to store the first occurrence index of each prefix sum. This helps quickly identify subarrays with a balanced sum. The prefix sum 0 is preceded with an index of -1 to handle cases where the subarray starts at index 0. A max_length variable is also initialized to track the maximum length of the balanced subarray found so far. We iterate through the array with a running prefix sum. If the current element is 0, we subtract 1 from the sum, otherwise, we add 1. This effectively treats zeros as -1s. For each prefix sum calculated, we check if it has been seen before in the dictionary. If it has, the difference between the current index and the stored index gives the length of the subarray. We update max_length if this new length is greater. If the prefix sum is new, we record its index in the dictionary. By the end of the iteration, max_length contains the length of the longest balanced subarray. This approach ensures that the solution is both time efficient, as it processes the array in a single pass, and space efficient, with the dictionary storing only unique prefix sums. Here, we start by importing the necessary packages and defining our solution class. The main method here is findMaxLength, which takes an integer array nums as input. The goal is to find the maximum length of a contiguous subarray with an equal number of zeros and ones. To achieve this, we use a hash map called prefix sums to store the first occurrence of each prefix sum. This map helps us efficiently track when the running prefix sum has been seen before. We initialize this map with a key value pair of 0 mapped to -1, which accounts for cases where the subarray starts at the very beginning of the input. We also define two variables, maxLength to keep track of the maximum length of such subarrays and prefix sum to calculate the running prefix sum as we iterate through the array. Now, as we loop through the array, we update the prefix sum by decrementing it when we encounter a 0 and incrementing it when we encounter a 1. This transformation helps us treat the problem as finding subarrays with a net sum of 0. If the updated prefix sum already exists in our hash map, it means that the subarray between the first occurrence of this sum and the current index has a balanced number of zeros and ones. We calculate the length of this subarray and update maxLength if this new length is greater than the previous maximum. On the other hand, if the prefix sum is not already in the map, we store the current index as its first occurrence. This ensures that we always use the earliest index for calculating subarray lengths, which is crucial for correctness. After completing the loop, the method returns maxLength, which represents the length of the longest balanced subarray. This implementation is efficient, with a time complexity of O(n), due to the single traversal of the array and the constant time operations of the hashmap. To understand this problem better, let's begin with the first example where the input is 0, 1. In the initial state, we have prefix underscore sum set to 0, -1, which helps us track the prefix sum indices. The max underscore length is initialized to 0, and the prefix underscore sum starts at 0. Now, for index 0 where the number is 0, we treat it as -1, so the updated prefix underscore sum becomes 0, 1, which is -1. Since -1 is not in prefix underscore sums, we add it along with the current index, updating prefix underscore sums to 0, -1, -1, 0. Next, at index 1, the number is 1, so we add 1 to the prefix underscore sum, making it -1 plus 1, which brings it back to 0. This time, 0 is already in prefix underscore sums at index -1. The subarray length is calculated as 1, -1, which equals 2. We update max underscore length to the maximum of its current value, 0, and 2, resulting in max underscore length equals 2. At the end, the max underscore length is 2, which is also the output for this example. Now let's move to the second example where the input array is 0, 1, 0. The initial state is similar, prefix underscore sum starts as 0, -1, max underscore length is 0, and prefix underscore sum is 0. At index 0, the number is 0, treated as -1, so prefix underscore sum equals 0, 1, which is -1. Since -1 is not in prefix underscore sums, we add it with the current index, updating prefix underscore sums to 0, -1, -1, 0. At index 1, the number is 1, so we add 1 to prefix underscore sum, making it -1 plus 1 equals 0. Here, 0 is already in prefix underscore sums at index -1. The subarray length is 1, -1, equals 2, and updating max underscore length gives max underscore length equals 2. At index 2, the number is 0, treated as -1, so prefix underscore sum equals 0, 1, which is -1. This time, -1 is already in prefix underscore sums at index 0. The subarray length is 2, 0 equals 2, and max underscore length remains 2. The final output for this example is also 2. In this slide, we conclude the second example, where the max underscore length remains 2, and the output is 2. Now, let's move on to a more complex example with the input 0, 1, 1, 0, 1, 0, 0. Once again, we initialize prefix underscore sums with 0, -1, to track prefix sums, set max underscore length to 0, and start prefix underscore sum at 0. With this setup, we're ready to analyze the array step by step to find the longest contiguous subarray with equal numbers of zeros and ones. Starting with index 0, the number is 0, which we treat as -1. This updates prefix underscore sum to 0, 1 equals -1. Since -1 is not in prefix underscore sums, we add it along with the current index, making prefix underscore sums equals 0, -1, -1, 0. At index 1, the number is 1, so we add 1 to prefix underscore sum, resulting in -1 plus 1 equals 0. Here, 0 is in prefix underscore sums at index -1. The subarray length is 1, -1, equals 2, and max underscore length becomes 2. At index 2, the number is 1 again, so we add 1 to prefix underscore sum, making it 0 plus 1 equals 1. Since 1 is not in prefix underscore sums, we add it with the current index, updating prefix underscore sums to 0, -1, -1, 0, 1, 2. At index 3, the number is 0, treated as -1. This updates prefix underscore sum to 1, 1 equals 0. Now, 0 is in prefix underscore sums at index -1. The subarray length is 3, -1, equals 4, and we update max underscore length to 4. At index 4, the number is 1, so we add 1 to prefix underscore sum, making it 0 plus 1 equals 1. This time, 1 is already in prefix underscore sums at index 2. The subarray length is 4, 2 equals 2, so max underscore length remains 4. Finally, at index 5, the number is 0, treated as -1, updating prefix underscore sum to 1, 1 equals 0. Here, prefix underscore sum equals 0 is in prefix underscore sums at index -1. The subarray length is 5, minus 1 equals 6, and updating max_length gives max_length equals 6. At index 6, the number is 0, again treated as minus 1. This updates prefix_sum to 0, 1 equals -1. Since minus 1 is in prefix_sums at index 0, the subarray length is 6, 0 equals 6, and max_length remains 6. In the final state, max_length is 6, which is the output for this example. This demonstrates how the algorithm efficiently calculates the longest contiguous subarray with an equal number of zeros and ones by leveraging the prefix sum approach and a hash map for quick lookups. The time complexity of this solution is O(n), where n is the length of the input array. Let's break this down step by step. First, we initialize a dictionary called prefix_sums, along with two variables, max_length and prefix_sum. These initialization steps involve only constant time operations, so they contribute O(1) to the overall complexity. Next, we iterate through the array nums using a for loop. This loop runs exactly n times, once for each element in the array. Within each iteration, we perform several operations, updating the prefix_sum variable, checking if the prefix_sum already exists in the dictionary, updating max_length if necessary, and potentially adding a new entry to the dictionary. Each of these operations takes constant time on average, meaning that the total time spent inside the loop is O(1) per iteration. When we multiply this by n iterations, the total time for the loop is O(n). Finally, once the loop has completed, we return the value of max_length. Since returning a single value is a constant time operation, this step contributes O(1) to the overall complexity. Combining all these steps, the total time complexity of the solution is dominated by the O(n) loop, making the overall time complexity O(n). Now, let's analyze the space complexity. The dictionary prefix_sums is the primary contributor here. It stores the first occurrence of each unique prefix sum encountered while iterating through the array. In the worst-case scenario, where all prefix sums are unique, the dictionary could grow to contain n+1 entries, including the initial entry of 0, -1. This means the dictionary requires O(n) space. Apart from the dictionary, the algorithm uses a few variables like max_length and prefix_sum, which take constant space. Therefore, these variables only contribute O(1) to the space complexity. When we combine these factors, the overall space complexity becomes O(n). In summary, the solution's space complexity is determined primarily by the dictionary, resulting in O(n) space in the worst case. To understand the efficiency of this optimized approach, let's compare it to a brute force alternative. A naive approach would involve checking every possible subarray to determine if it contains an equal number of zeros and ones. This would require two nested loops to generate all subarrays, which takes O(n² time, and an additional loop to count the zeros and ones in each subarray, which takes O(n) time. Multiplying these, the brute force approach has a total time complexity of O(n³), making it impractical for large inputs. However, its space complexity is O(1), because it does not use any additional data structures. In contrast, the current solution uses the prefix sum technique with a hash map, reducing the time complexity dramatically to O(n). While this optimization increases the space complexity to O(n) due to the hash map, it is a worthwhile trade-off for handling large arrays more efficiently. Now, let's analyze the performance of this solution under different scenarios. In the best case, the entire array forms a balanced subarray, and all dictionary operations, such as lookups and insertions, take constant time. This results in a time complexity of O(n) and a space complexity of O(n). For the average case, we assume a random distribution of zeros and ones in the array. Even with a mix of existing and new prefix sums, the dictionary operations still average out to constant time. This means the time complexity remains O(n), and the space complexity is also O(n). In the worst case, all prefix sums are unique, which means the dictionary grows to its maximum size with n+1 entries. Even in this scenario, the dictionary operations maintain their average O(1) time, so the overall time complexity is still O(n). The space complexity, however, also reaches its maximum of O(n), as the dictionary stores all unique prefix sums. To mathematically confirm the time complexity, we focus on the key operations within the loop, dictionary lookups and updates. These are highly efficient, averaging 1 time due to the hash map's constant time behavior for these operations. Since the loop itself runs exactly n times, and each iteration involves constant time operations, the total time complexity is n multiplied by 1, which simplifies to n. As for space complexity, the dictionary is the main contributor. In the worst case, it stores up to n plus 1 unique prefix sums, leading to a linear growth in space requirements. This results in a space complexity of n. Together, these analyses validate the efficiency of the solution, making it highly performant for large input arrays. Let's start by identifying some common mistakes that arise when solving the contiguous array problem. One frequent issue is misunderstanding the concept of subarrays. Remember, subarrays are contiguous sequences within the array, meaning the elements must maintain their original order without any gaps. Confusing subarrays with subsets, which can be non-contiguous, leads to invalid solutions. Another mistake is trying to count the zeros and ones directly for every possible subarray. While this approach might seem intuitive, it's highly inefficient, with a time complexity of n cubed for larger arrays, and it completely disregards optimization techniques like prefix sums. Additionally, many forget to account for edge cases, such as arrays that are empty, contain only zeros, or only ones. Ignoring these can result in incorrect outputs or even runtime errors. Finally, even when using the optimized prefix sum approach, errors often occur in updating the hash map. For example, failing to properly store cumulative sums can cause valid subarrays to be skipped. These mistakes highlight the importance of both understanding the problem's requirements and implementing the solution carefully. Another common difficulty is misinterpreting the time complexity of different approaches. Some might assume the brute force solution is adequate for larger inputs. However, with its n cubed complexity, brute force becomes impractical when the array size grows, such as when n reaches 10,000. Now, from an interview perspective, there are several key insights to focus on. First, be ready to explain the pattern of how prefix sums and hash maps work together to optimize time complexity. This is a recurring technique in many array problems. Second, it's essential to communicate the trade-offs between brute force and optimized methods. While brute force is straightforward, it's inefficient. On the other hand, optimized approaches require a deeper understanding of concepts like hash maps. Another critical point is recognizing that this problem can be reduced to a prefix sum problem by transforming the array. Treating zeros as negative ones makes it easier to track equal counts of zeros and ones. Lastly, always address edge cases in interviews. For instance, discuss how your approach handles arrays of length 0 or 1, or arrays without any valid subarrays. This demonstrates thoroughness and a strong grasp of problem solving. Now let's explore related problems and alternative approaches. Several LeetCode problems share similarities with the contiguous array problem, making them excellent practice. For example, problem 560, subarray sum equals k, uses prefix sums and hash maps to find subarrays with a specific sum. Problem 1248, count number of nice subarrays, focuses on subarrays with an odd number of elements, often solved with sliding windows or prefix sums. Of course, the contiguous array problem itself is a prime example, as it deals with balancing zeros and ones. Another related problem is LeetCode 930, binary subarrays with sum, which targets binary arrays and subarrays summing to a specific value. When it comes to solving these problems, there are two main approaches to consider. First is the brute force method, which checks all possible subarrays. While simple to implement, it's highly inefficient for large inputs, with a time complexity of n cubed. The second approach is using prefix sums with a hash map, which involves transforming zeros into negative ones and tracking cumulative sums. This method is efficient, with n complexity, but it assumes a clear understanding of data structures like hash maps and how to apply them. Finally, let's discuss an alternative approach that can occasionally be applied, the sliding window technique. This method is particularly useful in variations of the problem that involve fixed-length subarrays or other specific constraints. Sliding windows operate in n time, as they adjust the start and end points of the window dynamically to maintain the desired properties. However, it's worth noting that this technique is less intuitive and has limited applicability to the contiguous array problem as stated. For example, while sliding windows excel in problems with stricter constraints, they don't naturally align with the requirement to track equal counts of zeros and ones over arbitrary subarray lengths. Understanding when and why to use sliding windows versus other methods, like prefix sums, is an important skill to develop for tackling variations of this problem effectively. Great job making it to the end. In summary, we tackled the contiguous array problem using a hash map for prefix sums, achieving an efficient O(n) solution. Remember, mastering problems like these builds a strong foundation for tackling more complex challenges. Thanks for watching, and be sure to like, subscribe, and join us for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!